Hello students, welcome to Sri Jayendra's Rank Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 6 of a unit semiconductors. So let's begin with today's class. In today's class we are going to discuss about the transistors. So let's begin with today's class. When we say a transistor, it is basically made up from a two words. So when we say transistor, it is basically it is of transfer plus resistor. So it is in reality transfer of resistor, and that's why it has been the transistor. It is having a three doped regions that form two p-n junctions between them. And when I say transistor, it is having a three terminals. One of them, it's an emitter, another one, it's a base, and one more, it's a collector. So basically it is made up of three terminals. One of them is the emitter, another one, it's a base, and the third one is the collector. When we say emitter, this is the segment on one side of the transistor of moderate size, and it is heavily topped. And its main function of emitter is to supply majority charge carriers, or either it could be a electrons or it could be a holes to the base. The next is the base, and it is the central segment of a transistor. It is very thin and lightly doped region, and the main function of base is to pass most of the injected charge carriers to the collector. Now let's look what collector is. This segment collects a majority portion of the majority charge carriers that has been supplied by the emitter, and it is moderately doped and larger in size as compared to the emitter. And the main function of collector is to collect majority charge carriers through the base. So this is the basic details of this three terminals, that we are having three terminals. They are the base, emitter and collectors. And when we say we are having the three terminals, base, emitter and collector, let's summarize their situations. This is emitter, base and collector. So let's discuss them first from the size point of view. The size of the emitter, is moderate. The size of the base is the least, and the size of the collector is the highest. Let's discuss doping point of view. The emitter is highestly topped, the base is least topped, and the collector it's a moderately topped. Let's talk about the resistivity. As we understand that more the topping, more the conductivity, or we can say less the resistivity. Yes, so emitter, as it is having the highest topped, it is having the resistivity which is least. Base is least topped, so it is having the highest resistivity. And the collector as it is moderately topped, it is having the moderate resistivity when we compare this three. So this is the summary sheet which defines the role of emitter, base and collector, that so that we can have a rough approximation that this particular part will behave something like this. I hope this is clear. Is it? Great. Now let's have a look at certain quick questions. The main function, the main function of emitter is, emitter supplies majority charge carriers to the base. Yes, this is correct answer. To pass most of the injected majority charge carriers to the collector. No, this will it will pass on by the base. Supply majority charge carriers to the collector. No, no. So for A would be the correct answer. Second, the main function of base is supply majority charge carriers to the base. No, it's to pass most of the injected majority charge carriers to the collector. Yes, this is the correct option. So now let's look at the different types of transistor. Let's have a look what are the types of the transistor we are having. So basically we are having a two different types of transistors. One is the NPN transistor and the another one is the PNP transistor. When we say NPN transistor, in this transistor two segments of N type semiconductor, we can say emitter and collector, are separated by a segment of P type semiconductor. We can call it's a base. And while we talk about the PNP transistor, in this transistors two segments of P type semiconductor, they are the emitter and the collector, are separated by segment of N type semiconductor. Let's have a look schematically that how the NPN and PNP look. So this is the schematic representation of NPN transistor. This is the N type material, this is the P type, this is the N type. This terminal is known as the emitter, this is the base, and this is the collector. So this is the schematic representation of NPN transistor. As you can see this, that base, as we have discussed, it is very thin, so it is very less in dimensions. Emitter, and while we compare emitter and collector would be larger in size. So always whether it could be an NPN or it could be an PNP, the collector would be larger in size as compared to the emitter. While you draw even the transistor, please always keep this in mind that collector should be the larger one. Let's look at the schematic representation of PNP transistor. That this one is the emitter, P type material, N type material, and P type material. This is the emitter, this is the collector, and this is the base. And base, it's least in size. Emitter, it's a moderate in size, while the collector is having the maximum size. This was the schematic representation. And now let's look at the circuit symbols of NPN and PNP transistors. As you can see this, there is a three terminal device. Basically it's an emitter, base, and collector. And when it's a three terminal device, there is a one arrow. You can see this, there is a one arrow on the emitter terminal, that is for always. Yes, now based on the direction of the arrow, we will define it that whether it is an NPN or whether it could be a PNP transistor. You can remember it that if it is an NPN, then the arrow will represent the outside the transistor. Yes, this is the approach to see outside the transistor. And if transistor is of PNP type, then the arrow on the emitter would be there, but it will be within the transistor. This is the inside the transistor. Again, that's an emitter, collector, and base, and this is the PNP transistor. I hope this is clear. Is it clear? Is it? So do you have any doubts? Is there anything? Is there? Are you sure? Great. So the arrow indicates the direction of conventional current flow. Always keep this in mind. Again, this is the schematic view, that is it. This is the PNP transistor, and when it's a PNP transistor, on the P region it is the holes, they would be the majority charge carriers. When we talk about the N regions, they are the electrons. They are the electrons which play as a majority charge carriers, and minority charge carriers will be the hole. Same thing is true for the NPN material, that for both the ends, we can say it's an emitter and collector. Electrons will be the majority charge carriers of the region, while for the p-type material, holes will be the majority charge carriers. Now let's have a look to the quick questions quickly. In the circuit symbol of transistor, the arrow on the emitter indicates the direction of the flow of electrons. No. The direction of the flow of conventional current. Yes, this is correct. The direction of flow of holes. No. Both no. So this would be the correct option. Next, in a transistor, emitter is heavily topped. Correct. Collector is moderately dropped. Yes. Base is slightly dropped. Yes. All of this. Yes. Absolutely correct. So this is the correct answer. I hope this is clear. So now, up till now, we have already learned that what transistor is, what are the terminals does it have, how it should look based on the size, based on the doping, based on the resistivity, and we have also seen the schematic view as well as circuit diagram, a symbol of a transistor. Now we will be focusing on the working of transistor. For an example, we have taken an example of the working of PNP transistors on a same way. On a same way, NPN can work. So let's have a look. This is the we can say it's a cross-sectional view of the PNP transistor. This part is the emitter, this region is the base, and this region is the collector. And to this part we have provided the biasing too. And now you are aware that what biasing is, that whatever the supplies or whatever the resistance we are attaching to the circuits from the external world, they are known as the biasing of the circuits. So as you can see this, that one of the battery has been connected over here and other battery has been connected over here. This battery is known as VEE, and this is what we know as the VCC, and certain current is flowing through this. As you can see this, that current is the IE, it's an emitter current. Here the current, that is what we call as a IB, it's a base current. And here it's an IC, which we call as a collector current. So let's see how this will work. So what we are supposed to do is that this is the NPN, and when I say this is an arrow is there, that means it's an emitter. This is base, this is collector. Now as you can see this, that this is the p-type material. Let me show you that this is the p-type material has been connected with the positive terminal of the battery, and the n-type material connected with the negative terminal of the battery. So this junction, it's a junction of base and emitter. When we say junction, it is basically a location where two or more than two people are going to meet. So here it's a junction of base and emitter is forward bias. Now let's look at this. It's an n-type material connected with the positive terminal of the battery. So this is the reverse bias. Yes, so collector emitter junction is reverse bias, or we can say it's an so the emitter and base junction is forward bias with positive end of the battery to the emitter and negative to the base, as well as the collector and base junction is reverse bias with collector negative with reference to the base. The holes in the emitter, as it was the PNP type, as you can see it also here, yes, that the holes in the emitter P region are repelled by the positive polarity, and after crossing the emitter base junction enter the base region. Now flow of the hole in the emitter region, basically it is something like this, that this is the situation. It's a P and P, this is emitter, this is base, and this is collector. So flow of the holes in the emitter region constitutes the emitter current, that is what we call as an IE. And as we understand that base is very lightly topped, so the majority of the holes drift across the base, without combining with the electrons, because it is lightly doped. That means it is having the very high resistivity. So except a few that are the lost by recombination constituting the base current IB, but majority of the holes penetrates through the collector junction and it will enter to the collector region. So the collector terminal at the right end rapidly sweeps the hole that enter the collector region, causing a very large amount of current. That is what we call as an IC. So a continuous supply of holes injected into the emitter junction flows across the base to the collector. So the situation is in a PNP transistor. Majority charge carriers inside the circuits are the holes and outside the circuits are the electrons. So the relation between emitter current IE, base current IB and collector current IC is given by this IE is equals to IB plus IC, and we can say that this is universal relation for transistor. When I say this is the universal relation for the transistor, it means this relation is true for every situation and every configuration. You can always use this, you can always use this irrespective of the configuration or irrespective of the biasing and all of that. So when and when transistor could be there, you can use it. It is as simple as that, and that would be equals to IE would be equals to IB plus IC. Please note this. Have you noted this? Have you? Did you note this? Are you sure? Great. So let's look at the questions. In PNP transistor, majority charge carriers inside the circuits are blank and outside are the electrons. So in PNP transistor, majority charge carriers inside the circuits are the holes. Next, the relation between the emitter current IE, a base current IB and collector current IC can be given as that IE will be equals to IB plus IC. Next, NPN transistors are preferred than the PNP transistors because low cost, no. Low dissipation, no. Capable of handling large power, no. It's a high mobility of electrons than holes, and then high mobility of energy. Yes, because when we deal with the PNP, majority charge carriers in PNP is the holes, and in NPN it's electrons. Yes, so the mobility is higher and its mobility of energy would be the higher. That's why NPN transistor is preferred. NPN transistor is preferred over the PNP. Great. Next, in NPN transistor, the p-type crystal act as, yes, it acts as the base only. So have you done with this? Have you? Are you sure? Great. Now let's discuss something very important, that they are the different use of transistor. So how the transistor can be used. When and when I have been asked to use a transistor, basically transistor is having mainly two tasks. One is to amplify, that means as an amplifier, and second, transistor can be used as a switch. Now what amplifier means, that let's suppose that this is your input signal. We have given to this, we have given to the transistor, that means technically amplifier, and after it has been passed through the amplifier, it would look something like this. This is the original task of amplifier. I hope this is clear. Switch, you know, but in the switch even two category of operations would be there. One is the on switch and other is the off switch. When we say it's a on switch, that means current should pass to it. Or when it's an off switch, that means current should not pass through it. So on switches we understand a little, but amplifier it's a new for us. Now the question is how transistor would come to know that today I'm going to work as an amplifier or today I'm going to work as a switch. Even in the switch I will work as a on switch or I will work as the off switch. How transistor will come to know? So to guide the transistor we have a different biasing of transistors, because how transistor will come to know that I will work for today on this for this particular task. So we have three different biasing of the transistor, because we are having the three tasks basically. So when transistor works as an amplifier, we have two junctions. When we say it's an input junction and it's an output junction. So when I want my transistor to work as an amplifier, then the input junction should be a forward bias and output junction should be a reverse bias. When I want my transistor to work as a switch but in the on state, then what I want, I keep my for input junction as a forward bias and I will keep my output junction as the reverse bias. When I want my switch to work as an off state, my input junction will be the reverse bias and even the output junction will be the reverse bias. So this biasing of a transistor will let it know that yes, today you are going to play for the amplifier, today you are going to play a role of switch in the on state, today you are going to play a role of switch in the off state, and so on. I hope this is clear. Now based on these three categories, we have three different regions of the transistor. Even we are going to discuss it on later on, but please keep this, remember that when transistor work as an amplifier, it works in the active region. So when transistor work as an amplifier, it works in the active region. When transistor works as the switch in the on state, it works at the saturation region. This is the saturation region. And when it is in the switch off, it's a cutoff. It will work as the cutoff region. I hope this is clear. Is it clear? So if you have not noted it down till now, please noted this, that how the transistor will work as amplifier, or how the transistor will work as the switches, or how the transistor will work as the switch off. Yes, have you noted it? Did you noted this? Are you sure? Are you? Great. Now let's discuss how the transistor can work as an amplifier. In first, we will begin our study of transistor as an amplifier with a very simple schematic that will help us to understand that how transistor can work exactly as an amplifier. So basically, for transistor we know that IE is equals to IB plus IC, where IE, it is the base current, IB, oh sorry, IE is the emitter current, IB, it's a base current, and IC, it is the collector current. We know that IB is very less, and when I say IB is very less, IB is approximately 2 to 3 percentage of IE. So IB is just 2 to 3 percentage of IE, and that means we can say that IC is approximately 97 to 98 percentage of IE. So what we can understood is IE is approximately equals to IC, and let's understood this as an input current and this as an output current. Let's assume that this is the input current, this is the output current. Even reality is that we will IE would be on the input side of the circuit, while the IC, the collector current, will be on the output side of the circuit. So now let's discuss that when transistor works as an amplifier, its input junction will be forward bias and output junction will be reverse bias. So its input junction, it's a forward bias, and the output junction, it is the reverse bias. So the situation would be that this is the input, this is the amplifier, and this is the output. When I say this is the input, this is in forward bias. So if I took, it's a V is equals to I into R. This is RF, forward bias resistance, and this is the reverse bias resistance. It's a V in. This is V out. That is equals to I multiplied by RR. Why I have written I? Because it's an IE approximately equals to IC, and IE can work as an input resistance and our input current, and IC can work as the collector current. So this I approximately equal, it's almost 97 to 98 percentage, it is almost equal. Now in reality, forward bias resistance is approximately of 100 ohm, and the reverse bias resistance is approximately equals to 1 mega ohm to several mega ohms, let's say 10 or 100 mega ohms. So when I say it's a V in, it is equals to I as the current multiplied by 100 ohm of resistance, and when we say V output, then it is I as the current multiplied by 1 mega ohm. Let's take the minimum possible resistance, that is of 1 mega ohm, and when we say it's a 1 mega ohm, that is equals to 10 to the power 6. So if I took a ratio of this, it's a V out by V in, that is equals to I into 10 to the power 6 divided by I into 10 to the power 2. So this has gone, and this is equals to 10 to the power 4. So this is V out is 10 to the power 4 times V in, and this is what the requirement of amplifier is. That let's suppose if I have been provided a input junction or input function like this, then its output should be something like this. This is what the requirement, this is the requirement of amplifier. I hope this is clear, and even you now you know that how this will work, that V out is 10 to the power 4 times of V in. This is not true for every time, but this is how roughly transistor can work as an amplifier. I hope this is clear. So please always keep this, please always keep this in mind, and this will help you guys to understand the situation or to understand the reality that yes, transistor will work like this only. I hope this is clear. Is it? So do you have any doubts, any query over this? Is there anything? Is there? Are you sure? Are you? Do you have any doubts? Is there? No? Great. Now let's look at the basic transistor circuit configurations. We have basically three basic transistor circuit configurations. One is the common base configuration, another is the common emitter configuration, and the last but not the least, it's a common collector configuration. So we will start our discussion. We will start our discussion with the common base configuration. So let's begin our discussion as the common base configuration. So in this configuration, in the common base configuration, base is common to both input as well as output, and the base terminal is earthed, and the input is given across the emitter base, and output is taken across the collector and base, as you can see in the figure in the next slide. Let's have a look. So this will be the situation. Basically the requirement is, in transistor we have three terminals, and when we are having the three terminals, so to provide anything as an input, at least two terminals are required on the input side. At least two terminals are required on the output side. Let's say this is the input side, this is the output side. So at a minimum four terminals are required, two at the input side, two at the output side. But unfortunately, as a transistor we are having only three terminals. So how will we arrange this? So what we have decided is that we are going to keep any one of the terminal as a common, and when I say it's a common, that means it will be on the input side as well as it would be on the output side. So it would be on both the sides, on the input side as well as on the output side. So this is the common base configuration, where you can see this base is common to both. It is on the input side as well, it is on the output side as well. If you see the schematic, yes, this is the common base configuration, this is the emitter, and as arrow is saying, arrow is inside, it's a PNP transistors has been shown. So this is how common base transistor will look alike, that input side emitter and base would be there, and output side base and collector would be there. So base is common to both. I hope this is clear. Is it clear? Is it? Are you done? Are you sure? Do you understand this? Do you? Any doubts? Do you have any doubts up till now? No? Great. So now if I write all the parameters, that let's have a look, that This is the situation. Give me a moment. That this is the situation. This is the input junction. This is the output junction. And let's say even we are representing the PNP. This is the emitter. This is the base. This is the collector. Yes. So if I write down all the terms, then input current will be the IE, while on this side output current will be the IC. V input will be equals to I in multiplied by R in. V output will be equals to I out, that is generally IC, multiplied by R out. This R in is also sometimes called as the RE, and this R out is sometimes called as the R load resistance, or sometimes this people will call it as a collector resistance every time. It is something like this. So please noted this, please noted this. What we are supposed to do is that when we talk about the competitive examinations, they just rely on the formulas of the transistor, and they don't want any theory associated with the transistors. Even the board examinations have a very less focused on the theoretical part of the semiconductor devices. So please keep this in mind. Please keep the schematic clear in your mind, and you will be able to crack the questions. So please keep the schematic in your mind. Now now let's discuss first the current gain in common base mode. When I say current gain in CB mode, it is defined as the ratio of the small change in the collector current to small change in the emitter current. Basically it is the same, it's an output divided by input, but as it is about current, so it's an output current, or we can say change in collector current to the change in emitter current. And this is alpha, which is equals to delta IC divided by delta IE, and the value of the alpha is less than 1. Alpha is less than 1, and generally the value of the alpha is about 0.95 to 0.99. I hope this is clear. So this is the current gain. Now let's discuss about the voltage and voltage and power gain of CB mode. So let's first discuss voltage gain, generally denoted as AV, and basically it's a ratio of output voltage to the input voltage. When I say output voltage, it's an I output multiplied by R output divided by I input multiplied by R input. So this is equals to I output by I input. It's an IC divided by IE for the CB, and this is R output, RL by RIN. So IC by IE, this is equals to alpha times of RL by RIN. This is the voltage gain. This is equals to AV. This is the voltage gain. This is the voltage gain of transistor. I hope this is clear. Now let's discuss about the power gain. So power gain, it's a P output to the P input, and when I say it's a P output to the P input, this is I square output multiplied by R output divided by I square input multiplied by R input. So this is I square out by I square in. It's an alpha square multiplied by RL by Rn. This is the power gain of the CB common base configuration is. Please noted it. Please note this. Have you noted it? This is the power gain. Have you noted this? Yes? No? Yes? Great. So this was the common base configuration. This was the common base configuration of the transistor. Now let's look at the common emitter configuration. Common emitter configuration of the transistor. In this configuration, emitter is common to both input as well as output, and in this that the emitter is earthed and input is given across the base and emitter, and output is taken from the collector and emitter as shown in the figure. That you can see this is the PNP configuration, and here base is here, emitter is here, and collector is here. As you can see, this emitter is on both the sides, on the input as well as on output. That's why this is known as the common emitter configuration. If you want to see the schematic of it, it is something like this, that this is the base terminal, this is the emitter terminal, which is emitter terminal is on both the sides, on the input as well as on the output, and the output has been collected from this collector. So if I talk about the I input, that is equals to IB. If I talk about the I output, that is equals to IC. It's a collector current. If I talk about the V input, it's I in multiplied by R in, and when I say it's an I in multiplied by R in, this is equals to IB into RB. When I say it's a V output, that is equals to I output multiplied by R output, and when I say it's an I output, it is IC into RL. I hope this is clear. Is it? Any doubts? No? Please note this. Have you noted it? Have you noted it? Please note this. Have you done? Are you done with this? Are you? Great. So now let's discuss the current gain in CE mode. When I say C, it's a common emitter configuration mode. So current gain in CE mode is defined as the ratio of, it is the ratio of the small change in the collector current to a small change in the base current, keeping the collector and emitter voltage constant when the transistor is in active region. So basically beta, or the current gain, it's a change in collector current to the change in base current. You can understand this is the ratio of the output current to the input current. Output current in this case is the IC, so it's a beta, which is equals to delta IC divide by change in base current, which is equals to delta IB. So this is the beta, which stands to delta IC is to delta IB, and the value of the beta is about 20 to 200, because beta is always greater than 1. And we generally sometimes we have been asked that what is beta DC and what is beta AC. For us to perform the numericals, it is the same. When I say the AC, it is basically the ratio of the changes, and when it's a DC, it is the absolute values and no changes are required. So please keep this in mind. But at the end of the day, they are just the ratios of output current to the input current. I hope this is clear. Now let's first discuss the voltage and power gain. Voltage and power gain of CE mode. So let's first work for the voltage gain. It is the AV, which is equals to V output divided by V input, and when I say it's a V output divided by V input, this is the I output multiplied by R out divide by I input multiplied by R input. This is the I output divided by I input. This is equals to IC by IB multiplied by RL by R in. And this IC by IB, this is equals to beta multiplied by RL by R in. This is the voltage gain. Now let's discuss about the power gain. That this is the power gain. It's P output to the P input, and when I say it's a P output to the P input, this is equals to I square output multiplied by R out divided by I square input multiplied by R input. So this is equals to I square out divided by I square in. This is beta square multiplied by R out divided by R in, or I should say it's beta square multiplied by load resistance divided by input resistance. I hope this is clear. So please again note this. Do it quickly. Do it quickly. Have you noted it? Have you? Have you noted it? Are you sure? Are you? Yes. Great. Now we want to define one more term, and it is most favorite in the examiners. So people keep asking that, and it is the basically transconductance. This is transconductance. Generally it has been defined as GM. It's a transconductance. So this transconductance GM could be represented as, it is the ratio of output current to the input voltage. So basically it is the ratio of the output current to the input voltage, and when I say it's an output current, it's an I output divided by V in. I out, it's an IC. Input, it's an IB multiplied by RB. IC by IB, yes, it's a beta. So it's a beta divided by RB, or we can say it's a beta divided by R in. This is the transconductance. Please keep this noted. Have you done this? Have you? Are you sure? Great. Now let's derive one very important term. It is the relation. It is the relation between the alpha and beta. So as you have remembered that alpha is the current gain in this CB, it's a common base configuration, and this alpha could be given as it is equals to delta IC by delta I, and current gain in CE, it's a common emitter configuration, is this is beta, that is equals to delta IC by delta IP. So when I say beta, it's a delta IC divided by delta IB, or it would be the delta IC divided by delta IE minus of delta IC. If I took a ratio, it's a delta IC by I. That means if I divide this with delta I, that is delta IC by delta I upon 1 minus delta IC by delta I, and this is equals to alpha upon 1 minus alpha. I hope this is clear. So this is the relation of beta with the alpha. Even if you wish to find out the alpha, you can simplify it to the alpha is equals to beta upon 1 plus beta, or from this it's a 1 by alpha minus 1 by beta, that is equals to 1. I hope this is clear. So please note this. Please note this. Have you noted it? Have you noted it? Please note this. Are you done with this? Are you? Have you done it? Are you? Have you done it? Are you sure? Any doubts? Is there anything Any doubts? No? Great. Next is the common collector configuration. So in this configuration, collector is common to both input side and the output side, and the collector terminal is earthed and input is given across the base and collector, as you can see this, and output is taken across the emitter and collector terminal as shown in the figure. And it is, if we want to see the schematic of it, then it will look like this. Yes, it's a common collector circuit, but as we are rarely used it, because our syllabus is not covering the common collector circuit, so almost no numericals has been asked from this. So you just keep in mind the schematic, and if it requires, we can derive the relations from for this from the KVL, but generally they are not asking to this. Now let's look at this. This is very interesting diagram where you can find the examples of common base, common collector, and common emitter amplifier. That this is the common base configuration circuit. As you can see, this is the base which is common, and as it is a complex circuit because it is having a multiple capacitors and multiple resistors. Here what I want was that you only observe that what could be the situation when we deal with the common base or common emitter or common collector configuration, how they will look alike. Yes, so common emitter, look at this, emitter terminal is common on both the sides. Common collector, let's have a look. This is the collector which is common to both the sides. Both, when I say both the sides, I mean it is common to input as well as it is common to output. So please keep this in mind, and let's discuss one more but very important thing is that when transistor works as an amplifier in CB mode, the phase difference between input and output is 0 degree. That means it is something like this. Let's say this is the input, then its output, again it would be a curve of the sign, plus sign. But when transistor works as an amplifier in CE mode, phase difference between input and output voltage is 180. It's a 180 degree. So when I say it's an input, it is something like this. Let's say this is, let's say, the V input versus T, and when I say this is, we want V output, this is something like this. Let me redraw. Yes, there is a phase difference of 180 degree between input and output. Please keep this in mind. This is very important. I hope this is clear. So now let's look at the certain quick questions. Let's have a look. In CE common emitter configuration transistor, the current gain is less than 1. No. Greater than 200, not always, is always infinity. No. it lies between the 20 to 200. It is basically a beta, which is equals to delta IC divided by delta IP. Next, which of the following configuration has the highest voltage gain? Yes, let's discuss. We don't know about the CC, but what is CB configuration? This is basically V in, or let's write down directly the AV of the CB configuration. Then that was equals to alpha times RL by R in. And when we say it's a voltage gain of CE configuration, this is beta times of RL by Rin. Now we understand that beta is much greater than alpha, because generally alpha is less than 1, not much less than 1, it's less than 1, sorry, and beta can vary from 20 to 200. Yes, so the CE configuration has the highest voltage gain. I hope this is clear. Is it clear? Is it clear? Are you sure? Great. So we are winding up this session over here, but the transistor is still remain, and in the next lecture we are going to first discuss about the questions based on the transistor as an amplifier in a CB mode and in a CE mode. I'm going to break this lecture over here, because what I want that you just go through the session, note down all the formulas, revise the formulas, and when you tune into the next lecture, please be well prepared for that formulas as well as the information that we have talked in this lecture. So please go through this, because this is a very important topic when we are discussing about the NEET examination or J mains examinations. So it's a short kind of questions that this is going to be asked for sure. So please go through it, revise it thoroughly, if possible practice it, and come back for the next lecture. Till then, bye bye, have a good day, take care.